Hey makers and tech lovers, in today's video, we're building a custom DIY DeWALT battery pack, completely 3D, printed, spot welded, and powered by lithium-ion cells. We'll cover everything from choosing the right BMS to safely wiring your pack, and of course, testing it at the end. Let's dive right in. Before we dive into the build, let's break down the battery specifications. This pack is built in a 5S5P configuration, meaning 5 cells in series, 5S, to reach a nominal voltage of 18V, 5 cells in parallel, 5P, per group to increase capacity. That gives us nominal voltage, 18V, 5 times 3.6V, fully charged voltage, 21V, 5 times 4.2V, cutoff voltage, around 15V, 5 times 3.0V, total capacity, around 10,000 to 12,500 mAh, depending on the cells used, e.g. 5 by 2,500 mAh per group. This high-capacity configuration makes it perfect for demanding tools or extended runtime. The pack is protected by a smart BMS with balancing function and a built-in battery level indicator, so you always know how much power is left. To physically accommodate this, we printed the housing at double height, so all 25 cells fit securely and safely. We start with a fully 3D, printed battery housing, designed to fit standard DeWALT tools. To maximize capacity, we scaled the height of the model to double its original size, making room for a full 5S5P cell layout. It was printed in black PLA, but for better durability and heat resistance, I recommend using ABS, ASA, or polycarbonate. The Thingiverse link to the STL file is included in the video description below. Step 2. Selecting the right BMS. Next up is the BMS, the battery management system. We're using a 5S DeWALT-compatible BMS with built-in cell balancing and a handy battery level indicator, so you can always check the charge at a glance. In this configuration, 5 lithium-ion cells are connected in series, giving us a nominal voltage of 18 volt. That's 5 times 3.6 volt. You'll find the exact BMS I used linked in the video description below if you want to use the same one for your project. Step 3. Preparing the cell stack. Before doing any mechanical assembly, I inserted untested cells into the printed housing to verify the fit. Once confirmed, I removed them and began balancing the lithium-ion cells, bringing them all to around 4.0 volt plus or minus 50 mV to ensure safety and even charge distribution. After voltage balancing, I sorted the cells by capacity. Blue cells is almost equal to 2100 mA, purple is almost equal to 2000 mA, yellow is almost equal to 2500 mA. Each parallel group consists of a mix of these to even out total group capacity, and we repeat this 5 times. Step 5. Spot welding. Time to spot weld. Before committing to your actual battery pack, always test the weld quality using a demo spot weld setup with scrap cells and nickel strips. This helps ensure your machine settings are dialed in and avoids ruining good cells. In my case, those tests revealed that only the yellow LG cells could be welded properly with my spot welder setup. The purple and blue cells didn't take the welds well, likely due to the casing alloy or surface coating preventing solid connections, so I decided to reuse the yellow LG cells from a previous DIY battery project and use the purple and blue ones for that pack. Before welding, I thoroughly cleaned both the cell terminals and the nickel strips to ensure good contact and reduce resistance. Machine configuration. Use short pulses, 3 to 5 milliseconds, at 70 to 90 joules, adjust based on your spot welder, apply firm but not excessive pressure to the electrodes, make full contact without denting the cells, test first on scrap cells to find ideal pressure. Wait 5 seconds between welds for heat dissipation, never exceed 6 welds per cell at once because of overheating risk. For my battery pack project, I deliberately chose to make at least 3 spot welds per connection as a safety precaution. This approach provides several critical advantages for building reliable high-performance battery packs. The multiple welds create redundant connections. If one weld happens to be suboptimal, the others maintain solid electrical contact. This is particularly important for applications involving vibrations or thermal expansion. The additional welds also help distribute current flow more evenly across the contact surface, reducing the risk of localized hot spots that could lead to failure points. Before working on the actual battery pack, I conducted extensive test welds to dial in the perfect parameters. Through systematic testing, I learned how different variables affect weld quality: cell terminal coatings, nickel-plated versus bare, nickel strip thickness and composition, optimal power settings for my specific spot welder. The nickel strip overhangs were bent around the cell edges, and I added insulating tape over the outer cells to prevent short circuits. For anyone attempting similar projects, I strongly recommend always testing on scrap materials first, documenting your optimal settings for each material combination, never compromising on the number of welds per connection. Remember, in battery pack construction, there's no such thing as being too careful. Those extra spot welds and test procedures could mean the difference between a pack that lasts for years versus one that fails prematurely. My quality control process includes visual inspection of each weld for consistent penetration, mechanical stress testing of sample connections, resistance measurements across contacts. While this thorough approach takes more time up front, it's absolutely critical for building safe, long-lasting battery packs. Step 6. Bridge planning. Welding. After welding and inspecting all contacts, I planned out the bridge connections and mapped out a contact layout for the BMS. For this task, I studied the BMS, Battery Management System, labeling and created a wiring diagram, first on a sheet of paper and then directly marked on the battery pack itself for clarity during assembly. After finalizing the layout for the series connections, I moved on to preparing the bridge components. For each serial bridge, I plan to use 2 separate bridge elements to ensure a solid and reliable connection. To make these, I carefully cut strips from a sheet of nickel-plated contact material. Each strip was sized to handle the current requirements, so I ended up with 3 to 4 bridge segments per connection. I made sure each cut piece was clean and free of burrs, as even small imperfections could lead to uneven current flow or hotspots. Since every serial bridge required 2 of these pre-cut strips, I double-checked the measurements before moving forward. This way, I could maintain consistency across all connections and avoid any weak points in the battery pack's wiring. Once all the strips were ready, I aligned them precisely over the cell terminals, ensuring proper overlap for a low-resistance joint. The goal was to keep resistance minimal while maximizing mechanical strength, especially important in high-current applications. Each bridge was made from sliced nickel strip, giving me around 3 to 4 bridges per strip. To handle higher current flow, I used 2 bridges of nickel per connection, then welded them into position. After all bridges were secured and the total pack voltage checked out correctly. Step 7. BMS installation. Wiring. I began by tinning all the battery contact pads with solder to ensure solid, low-resistance connections. I carefully inserted the entire battery pack back into the 3D printed housing. Inside the housing, then I carefully mounted the BMS directly onto the battery pack, aligning it with the contact layout created earlier. The soldering process started with the main negative terminal, very happy face, using a blue wire. From there, I connected each balance lead in sequence, B1, B2, B3, B4, making sure the order matched the 5S configuration. Finally, I soldered the main positive terminal B+. Once all connections were made and double-checked, I insulated both main contacts using electrical tape, adding an extra layer of safety and minimizing the risk of short circuits. Step 8, Final Assembly. With all components securely in place, I proceeded to install the battery level indicator into its slot in the housing and fixed it in position using hot glue for a snug, vibration-resistant fit. Next, I closed up the pack by attaching the top cover with 4 M3 10mm screws, ensuring a firm and stable enclosure. As a final safety measure, I applied a red insulating strip around the housings to enhance overall electrical insulation. And that's it. A fully functional, custom-built, 3D, printed DeWALT-compatible battery pack. We tested for voltage and continuity, spot welded a full 5S pack, mounted a BMS and built the housing from scratch. If you found this useful or inspiring, don't forget to like, subscribe, and share your battery builds in the comments. Catch you in the next one. Stay safe and keep building.
Don't forget to like and subscribe.